On the 7 series slice flip-flop. Hello, and welcome to this recorded e-learning on the 7 series slice flip-flops, part 1. My name is Frank Nelson. I'll be your instructor for this module. After completing this module, you should be able to describe the control sets of the slice flip-flops that are available to you. And also, you should be able to identify the implications of the control sets have on the packing of your finished design in your FPGA. Now, the contents of this module are broken into 2 different recordings. We're going to first talk about control sets, then we'll get into designing resets into your FPGA design, and then discuss other reset considerations as part of the second recording. The key is to realize that these tips will allow the implementation tools to group more logic together into slices, which allows greater device utilization and gives the implementation tools the best opportunity to find a better parsed solution that both meets your timing or performance objectives as well as higher device utilization. Now, this is compounded by the fact that often a poorly coded piece of logic creates a timing critical path for a designer to resolve, and often designers will end up wasting a great deal of time resynthesizing and repeating a place and route solution over and over in an effort to hopefully meet their timing constraints. Instead, what a designer should do is reevaluate their HDL coding techniques and the use of their control signals. Now, there's a couple of things you need to first understand about slice flip-flops. First of all flip-flops are D-type inside of the FPGA. So even though you can build JK or T-type flops in your HDL code, in essence, you're going to be building from a D-type flop. So building with those other types of flip-flops will only add extra logic to your design that should be unnecessary. Now, all flip-flops have a clock input that's denoted by the CK port. The clock can be inverted at the slice boundary as well, with that inverter being locally located. All flip-flops have an active high chip enable. So you'll want to be aware that if you design with an active low chip enable, then that will require an extra inversion on the lookup table output. All flip-flops have an active high set reset input as well. The set reset can be synchronous or asynchronous on the local flip-flop, so that is programmed locally, and this is determined by the configuration bit stream that is finished by the implementation tools. You also have the ability to set the flip-flop value to a predetermined state as determined by the configuration bitstream as well, and this is chosen by default based on your HDL coding style. All flip-flops are also initialized during the configuration process by default. Now, this example is a good way to code for your FPGA's flip-flops clock enable port functionality, and as you can see, this is easily inferred using standard HDL coding practices. So you're simply going to have your clock enable not in your sensitivity list, first of all, and it will be placed in your secondary parenthesis to define the actual Q to D behavior of the flip-flop. Now, all flip-flops have that chip enable pin. It's active high, and it's synchronous to the clock. When inserted, the flip-flop clocks on the D input. When it's not inserted, the flip-flop holds the current value. You should recall that the 7 series has a single active high set reset port. That flip-flop with that set reset port can be configured as either a synchronous set or reset or an asynchronous preset or clear port, and that is defined purely by your HDL style. When asserted, the flip-flop output will be forced to that set reset value attribute of the flip-flop, which is inferred from your HDL. This attribute is extracted automatically based on the structure you use. So following good coding techniques for set reset is important to infer that value appropriately. The flip-flop also has an initialization value that's also inferred from your HDL code, and that is given the attribute init or init. This is the value loaded into the flip-flop during configuration, and when the global set reset, that's the GSR net signal, is asserted. The GSR travels to all the synchronous elements and resets them as part of the configuration process. This attribute can also be extracted again from your RTL code by some synthesis tools based on your coding style as well. Xilinx does not recommend the use of asynchronous resets, even though our devices support them. They simply invite too many designers to design asynchronously, and those designers usually regret that. So in this case, we wanted to point out to you, we have 2 examples of inference of your reset. And of course, since the reset is part of the sensitivity list, that means that process can become active without the actual rising edge of the clock signal. So we're going to be showing you examples here of an asynchronous reset behavior, which is not recommended. So the output will take the reset value immediately, even if the clock is not present. But what we're really trying to do with this slide is to show you how your synthesis tool will infer that value based on your code. So realistically, I recommend the use of an AND in the sensitivity list of this example to make sure it's a synchronous reset, or to remove the reset from the sensitivity list and put it nested below in the process. Now this example is showing how to synchronize an asynchronous reset with the rest of your FPGA design. In fact, this circuit is effectively designed to prevent metastable events that should be used if you're bringing in an asynchronous reset into the FPGA. So first note that deassertion of the reset should be synchronous to the clock. Not synchronizing the deassertion of the reset can create synchronous design problems, such as the flip-flops going metastable, or not all flip-flops guaranteed to come out of reset on the same clock. So we recommend the use of a reset bridge, like you see here, to synchronize the reset to your clock domain. Now this example demonstrates how to properly code for a synchronous reset of your flip-flops. And the first thing you'll notice, of course, is that the reset is not included in the sensitivity list, but is nested as part of the process. So this requires that the process only becomes active, or that the reset only becomes active when we have a rising clock edge. So effectively, this is an AND, rising clock edge and the reset being asserted. Now similarly, you could put an AND as part of the sensitivity list, and then you would also get that behavior. But the key thing is the reset pin of the flip-flop is a regular timing path endpoint. So the timing path ending at the reset pin will also now be covered by the use of a period constraint on your clock signal. This example shows how to code for initialization value. Most designers should do this to make their simulation easier. This assures that your simulation will not show an unknown state after starting a simulation. Instead, it will show the initialized value correctly. In this example right here, that would be a case of a 1. So it's important to keep in mind that when the FPGA is configured, the flip-flops are loaded with that initialization value, and that's determined or inferred by the init attribute based on your coding style. That value can be restored by asserting the GSR net as well at any time. The initial value of that signal that is used for the flip-flop is extracted by your synthesis tool. So in this case, you see that before we get to the process, we actually define a Q output value, which is inferred by your synthesis tool as a init attribute. Now note, this is a Xilinx specific capability of your FPGA, and it is something you should plan on using, especially if you plan to simulate your design, which virtually every customer is. Now, to be specific, control signals are, of course, sets, resets, clock signals, and a control set is a group of control signals that are used for one slice. Now, this is important to note because these control signals are shared among the different slices. Okay? So this is referred to as a control set. Clock enable and set and reset signals are active high by default. That means that the flip-flop is expecting them to be active high. If you're using negative edge of those signals, then of course you're going to need another inverter, which usually can be mapped as part of the lookup table if it's an equation derived, but it can be more complicated or use extra routing resources if it is not mapped from a lookup table. Now the clock can be inverted at the slice boundary. That inversion is free and that's dedicated. If any one flip-flop uses a clock enable, you should also know that all other flip-flops must use the same clock enable. So it's not possible to bring two different clock enables to the different flip-flops in that slice. So it's important that you try and allow the tools to try and group those synchronous elements based on the common control signals that are necessary for the circuitry. Now, the clock enable also provides a mechanism to save power because it decreases the number of transitions that you'll have in your design. So use of the clock enable is something that's recommended as part of a good synchronous design practice as well as to manage your power consumption. Also, if any one flip-flop uses the set reset signal, then all the others must use the same set reset, just like with the clock enable. Now, this is not a real cost to the consumer. We don't suddenly find that we have less device utilization by building that. But the key thing here is that this is done on the slice level. So if in the case you are developing low fan-out control signals that maybe only drive a few flip-flops, then you should be able to find the tools to group those flip-flops into the same slice to reduce the number of control signals that are distributed through your design. But we would always tell our customers it's always important to evaluate and reduce the number of control signals you have in your design and try to eliminate all your low fan-out control signals that maybe only go to teens or 20s or even low hundreds of flip-flops. In that case, it might be a really good idea to try and share as many control signals with other logic if at all possible. So always evaluate your control signal usage and try to manage their fan-out. So it's very important that designers remember to pay attention to the control signals they're inferring with their HDO code. This is especially important because the flip-flops in each slice share all the same control signals. Now this can prevent some flip-flops from being used in a slice if you have very low fan-out control signals in your design. But likewise, I'd also say it's very important for you to try and evaluate the control signals that you're planning on using for the cores in your design, particularly if you're instantiating a component from a core generator or system generator. You want to plan on trying to share those same control signals through the rest of your HDL in your design. But in general, 8 registers per slice, and all have to use the same control set. If the number of registers in a control set do not divide cleanly by 8, then some registers run the risk of not being able to be used, but that will depend upon the rest of your design. Now, this is a concern for designs that have lots of low fan control sets. A design with a large number of control sets potentially can show lower device utilization, but not always. That'll simply depend. Designs with a small number of control sets are preferable. The key is to evaluate the slices that have unused registers. Okay, so if you're using lots of lookup tables without using the register, you maybe want to go have a look at what function or component those lookup tables are part of, and try to evaluate the control signals that are used as part of those components. And try to build designs with common control sets as much as possible. It is important for you to remember that synchronous sets and resets, as well as clock enables, can be made for your design by routing to a LED input, rather than connecting to the corresponding port on the flip-flop. Now, this is part of the basic functionality of the lookup table. If we can drive the clock enable to the LED input and then take the output and drive it to the clock enable port, or not use the clock enable port at all, then we can actually build some additional functionality. So one of the nice things to keep in mind is the more you use synchronous sets and resets and clock enables, the more likely you have the ability, or given your synthesis tool the ability, to not use the dedicated port on the register for just that control signal. Instead, you could use it for an asynchronous reset or an asynchronous set if you need it. You'll also need to know that the set reset port can be programmed, again, as either a set or a reset, but not both. So if you're defining a design that has both a set and a reset on a single component, then one of those will need to go to the lookup table, which means it will have to be synchronous. Unlike older FPGA architectures, there's not a separate set and reset port available on these flip-flops. So if you want both, either the set or reset will have to be generated from a LED input and be synchronous. The set reset port can also be implemented as asynchronous, although this is not as flexible. An asynchronous set or reset port cannot be implemented as a LED input, so your synthesis tool and the implementation tools don't have the ability to map this control signal to a LED input. So it's one of those things that we would say, if you're building an asynchronous set or reset port, is that you should carefully evaluate whether you actually need it or if you can instead code it as synchronous. This slide demonstrates how the implementation tools benefit by the use of synchronous set and reset signals. In this case, these flip-flops can be placed in the same slice, since the set and reset inferred by your HDL code is synchronous. The implementation tools just migrate the set and reset to LED inputs rather than mapping them directly to the register ports. So what we're getting at here is, again, we have a much better chance of being able to group this component, if it's a low fan-out control signal, with other flip-flops or other logic of different functions into the same slice or CLB, simply because the set or reset and the clock enable are synchronous. So again, it's just a very good practice. It gives the tools a lot more flexibility, better device utilization, better chance of meeting your timing. Lots of good reasons to do this. So here we see an example on the left where the designer has built 2 different types of flip-flops, one with the clock enable, one without. By allowing the synthesis tool to move that clock enable to a LED input, effectively, as you can see in the right slide, or the right portion of the slide, that now that clock enable gets sucked up into a LED input, as well as the current status or the D port gets fitted in as a LED input. So the caveat here is we can pack these 2 registers in the same slice because now the control sets are identical. The caveat, of course, here is we lose some LUT inputs to this second flip-flop. So it's a good and a bad thing, but the key thing is if we build a synchronous set or reset or a clock enable, we want the tools to have this ability because it can improve our device utilization. Now likewise, the synthesis tool can be instructed to reduce the number of control sets in the design. And again, this is best done when you use synchronous sets and resets and clock enables in your design. By going to your synthesis tool, that's XST, and setting the value to auto, instructs the synthesis tool to reduce the control sets by converting synchronous set, reset, and clock enables to LUT implementations where appropriate or necessary. So in general, what I'd probably tell any customer is, before you set this, what was your synthesis result like? How many control sets did your design have? How many low fan-out control signals did your design have? Now you can find that kind of information from your map report and from your synthesis report as well as just understanding your design and looking at the schematic viewer representation of your design. So if you do have a high number of control sets, then this is something you can try, and it should help you in the case, especially if you're building with synchronous sets and resets. When planning your control signal usage for your flip-flops, keep in mind that the instantiation of cores or IP will also add additional control signals to your design. This is often forgotten by designers. So you have to first build your cores and look at the control signals you need in building those cores, and then you want to plan on trying to share those same control signals with as much of the HDL as possible. So try to share them, and we recommend that you build and simulate your IP as soon as possible from construction so you can plan on sharing your control signals appropriately. Likewise, if your design is large, plan on evaluating your synthesis results as early as possible, and always take the time to verify your synthesis tool generated the anticipated and appropriate control signals for application. And as I mentioned earlier, active low control signals are not recommended. This is because the flip-flops do not have local inversion available for your sets and resets and clock enable. And instead, inversion requires a LUT input. So this is important to keep in mind. Active high control signals are always best. So keep in mind that designing with active low control signals is an older design process or practice. So if you're emulating an ASIC or working with an older design that you're having to reuse, you might need to make some design changes right off the bat. In fact, we would strongly recommend that. Now this slide shows exactly the caveats to using active low control signals in a hierarchical design methodology. In this example, an older core, an older netlist, a partition, or hierarchical design methodology was used. And in this case of a hierarchical component, we would recommend resynthesizing the code with the design modification. In the case of a core, we would recommend regenerating the core. And if partitions are being used, the designer should consider resynthesizing and re-implementing the maintained portion of the design, simply because we're having to locally invert and use a LUT to not only add delay, but to waste a LUT simply to do the local inversion. Now keep in mind, if these control signals are high fan-out, this might be prohibitive in terms of the number of LUTs you're wasting. So always bear in mind, evaluate your control signals early in the design process, as early as possible. So here we have an example where we're really trying to get you to think about your control set design for your application. So we want to get you to think about this a little bit, and then we'll discuss the answers to these. In the first case, we have two flip-flops, different clocks, but the same clock enabled and set signal. Second case, we have same clock, one has a clock enabled, the other does not, and we have two different resets. Likewise, case number 3, we have same clock enable, but the reset is inverted between the two. And then the fourth one, we have the same control signals, clock enable, and reset. And so you really have to ask yourself simply, can these be paired into the same slice? Well, in case number 1, the answer is no. The flip-flops have different clocks, so they're members of different control sets and cannot be possibly grouped into the same slice. So that's just not going to happen. Case number 2, flip-flop 2 has a high, or VCC, as the clock enable. So even though we don't have a clock enable defined for the behavior, because one does and the other does not, that effectively defines there being separate clock enables. So likewise, those can't be grouped into the same slice as well. And then our third example with different resets, or with one being active edge, one being negative edge, the local inversion of the control signal is not supported, so these flip-flops are members of different control sets. And in fact, we would end up using a LUT input for that reset, if not an entire LUT. And then our last example, of course, These are ideal, where we have the same control signals and they can be grouped in the same slice because they have the same control sets. Now, as I mentioned, we'll talk more about control signal usage in the next recording, but first we're going to wrap up this recording, and then you can check out the part 2 version of this recording. Control set restrictions can reduce your design utilization, and specifically we recommend use of synchronous sets and resets, and of course clock enables. Your reset methodology can have a significant impact on your design efficiency, so it's important to evaluate what control signals your design has, what control signals your cores or other dedicated IP requires as well, and try to share those control signals as much as possible. For designs that are not pushing the limits of your device utilization or performance, it is recommended that synchronous resets be used for all storage elements. That's for memories as well as flip-flops and DSP slices. For more sophisticated designs, a mixed approach where only critical logic is explicitly synchronous reset and all other logic relies on the GSR is recommended. So specifically here we're talking about use your synchronous reset and then use the GSR, which is again a part of the configuration process where all elements are set or reset to a known state after configuration is completed, rather than having to actively reset the circuit frequent times. Also use asynchronous resets only when you're absolutely required due to the application. So keep in mind, if you can do it synchronously, it's always better. So now we're going to go and look at designing resets, and then we'll look at other reset considerations before wrapping up our discussion of the slice flip-flop functionality. So there's basically two types of resets, global resets and local resets. Global resets set all storage elements to a known state based on your global criteria of your design. This usually requires the assertion of an external reset pin, is what most customers will actually use, or else waiting for a PLL or MMCM to lock after configuration. And one of the first things to note here is our current Xilinx FPGAs, of course, will offer this feature automatically. So every synchronous element comes up into a known state and defaults to a reset state of 0 unless you program it otherwise. Local resets are internally generated signals that can cause some storage elements to be forced to a known state. So for example, a terminal count on a counter clearing the existing conditions would be a good example of that. But the key thing here is to note a local reset does not reset all the synchronous elements. That's the big difference here. And of course the caveat is a global reset can suck up a lot of wire, a lot of routing resources in the distribution of a global reset. So we try to minimize the number of global resets, but also manage the number of local resets your design has. That's going to be our goal going forward. Now, as I mentioned before, synchronous resets are always recommended. And a synchronous reset, local reset, is simply a part of a typical design. And again, this is typically built when you're generating to test for a condition of one or more flip-flops to be returned to a fixed state. And that reset should always be synchronous, as I mentioned. Now, synthesis tools are then free to use synchronous set and reset port as part of the implementation of the normal functionality, or likewise, they could even map it to the lookup table input. Asynchronous resets, though, use locally generated asynchronous resets is simply not recommended. Any glitch on the generated reset signal can cause unwanted clearing. A runt pulse on the generated reset signal can cause metastability as well. And likewise, in addition, these cannot be mapped to LUT inputs, so they're rather restrictive and their use is not recommended. Now, the use of a complete global synchronous reset does make very good design sense, and in this case, all storage elements are set to a known state using a synchronous set or reset port. Each clock domain of the device will then use that synchronized version of that global reset. Now, the advantages is simply it's easy to implement, it's foolproof, it allows synthesis tools to perform control set reduction if necessary. But the disadvantages include it not working in situations where the clock is not guaranteed to be running. Or also, the other secondary caveat is it uses substantial routing resources. Now, keep in mind that as part of the configuration process, we mentioned that a global reset is executed on a separate routing resource. So what we're really talking about here is in addition to that configuration and reset, the use of a global synchronous reset. So in general, we would tend to discourage this if at all possible, simply because it sucks up so many routing resources, and the fewer routing resources you have, the less chances you have to be able to meet your timing objectives. Now this slide is talking about using an extra global reset that is asynchronous. So you need to recall that in the previous recording we mentioned that if this is asynchronous, it needs to be synchronized so that it does not cause your circuit to go metastable. Now this is simply based on your global design. All storage elements will be set to a known state using an asynchronous set or reset port. And note, it can only be mapped to the flip-flop set or reset port. The advantage is it will work even if the clock is not present. It's required for systems that need to generate valid outputs even when the clock is not present, such as input interfaces from hot pluggable devices and interfaces using recovered clocks. The disadvantage, of course, is it cannot be part of a control set reduction. So since it's ported directly to the flip-flop port, this is often greatly limiting to the control set utilization in your design. And it also, like a global reset, will use substantial routing resources. So in general, global asynchronous resets are not encouraged as well. Now there's a couple of ways you can change your reset to a synchronous reset. Now, again, all new code should use synchronous resets when a reset is necessary. And that's because, of course, for simulation purposes and testing purposes, that is critical. But for existing code, you got a couple choices. Now, you can leave it alone and acknowledge the possible drawbacks of an asynchronous reset. So, of course, any glitches in your system that might be encountered or metastable situations you might still encounter down the road, those are not necessarily testable. So be aware of that if you choose to leave your code alone. Or you can use a synthesis switch, which is sometimes dangerous. Now note, this is not the same as changing your code to a synchronous reset, but this can make the synthesis result different from the behavioral simulation, which is also rather risky. Instead, we really recommend that you simply manually change or use a script to modify your HDL code to modify the asynchronous reset and convert it to a synchronous reset. You may also keep in mind that removing the top-level reset port does not get the same result as removing the reset from your code. You'll still have to modify the HDL behavioral code to remove that reset. Now this slide is showing an example where an additional global reset was used to route on general interconnect. So this would work in the case when you've built that global reset and yet you still also have that global reset that is part of the configuration process. In that case, you would physically have two resets on your design. So as you get an idea quickly, in just this simple case, that reset's going a lot of places and it sucks up a lot of routing. And as I mentioned, the more routing resources that disappear are limitations on the implementation tools so that they cannot always meet your peak performance objectives. So resets compete for the same resources as any active signal in your design, including timing critical paths. So bear in mind that having additional control signals, whether the resets, sets, or clock enables, that you do not try to reduce will suck up routing resources and may run the risk of preventing you from meeting your timing objectives. Now, as I mentioned, the startup block gives you access to the global set reset network. That's the GSR you see on the primitive component on the far right. Now, to learn more about this startup block, what I again recommend to you is to check out the Xilinx Unified Libraries Guide to learn more about its functionality. But the GSR is a special reset signal that is used to hold the design in a reset state while the FPGA is being configured. And as I mentioned, by default, during configuration, it is activated and it resets every synchronous element in your design. But what you can do is drive another signal to the GSR port, and what you can then do is anytime you want to reset your system, you can drive that GSR port, and it basically acts as an OR gate to all the synchronous elements in the design on the reset port. So after configuration is complete, the GSR is released, and all the flip-flops and other resources will now possess that initial value state. The deassertion of the GSR can take several clocks to affect all flip-flops in the design, and that's one of the big caveats, is the routing delay is not fast. So it can often take multiple clocks, and of course that builds in a system reliability issue in your application because the routing is not fast. The deassertion of the GSR is asynchronous to all system clocks as well, and that can't be customized. Now the GSR can be asserted again from fabric logic by instantiating this component in your design, and that'll allow you connection to the GSR net inside the FPGA. The benefit, of course, though, is it does save you routing resources if you need a global reset, but you have to be aware you can't control which elements get set or reset when you drive a signal to the GSR port. All the elements get reset. That brings the next question. How do you get by without using resets? We mentioned that as an option. Now, resets are generally used to initialize the design to a known state of power-up. But keep in mind, in FPGAs, that's already done for you and available to you by default. You can't remove that. So the key thing to understand is you have to understand the initialization state and the use of the GSR when it's used by default as part of configuration. You also control the starting up of the design after power up. That's another thing that you can also control at your leisure. So the more you know about configuration, the more you can actually hopefully design out any unnecessary resets in your design. The GSR ensures that all storage elements are at that known value. However, the GSR deassertion, again, is asynchronous and slow. And this is part of the reason why this is done as part of the configuration process. Recall, configuration takes a few milliseconds. So there's plenty of time there as part of configuration at the FPGA to actually reset everything in the design to that known state. But if you actively drive a signal onto the GSR, keep in mind, again, the routing is slow, and that could cause a metastable situation or create an illegal state in your logic that starts autonomously. In general, a mixed approach whereby the GSR is used to set the initialization state and an explicit reset is used to manage the startup on some components can be very efficient, and that's what actually most designers do. They'll take those few components they need to reset and make sure they're in a known state to begin with, and they might go ahead and either use the GSR for that, or else they might do a secondary reset after configuration to reset the component. Now let's take a few seconds and we're going to look at other reset considerations before doing a summary. It's very important to remember that one of the biggest reasons to use a synchronous reset is that certain dedicated hardware resources simply don't have and don't support an asynchronous reset. So if you code with an asynchronous reset, you may not be able to infer the best device resources. For example, to infer the DSP resource will require a synchronous reset to be coded. So if the user is going to infer a multiplier, it will have to include a synchronous reset in its behavioral code. Unfortunately, synthesis tools cannot infer all possible configurations of the DSP slice, so this will require you in many cases to instantiate the function you want from the core generator. The DSP slice will allow you to build the most useful arithmetic functions such as multipliers, adders, subtractors, multiply, and accumulators, as well as counters, including counters with a programmable terminal count, but also build comparators, shifters, large multiplexers, pattern matching functions, as well as other functions. Many designs that run out of slices are not fully utilizing their DSP slice resources. Synthesis tools will infer the DSP slice resources for multipliers, but they're not smart enough to infer other functions. Now you can control synthesis use with attributes, but not if an asynchronous reset is used. Likewise, many customers try to infer the block RAM resources and are disappointed when their synthesis tools don't allow them to build what they want. Well, this is a typical limitation of most synthesis tools. One of the benefits of using the block RAM is that it has a minimum clock to output time when the output register is used. But what designers don't realize is that, like the DSP slice, the block RAM does not allow inference of an asynchronous reset. This is because there is simply no asynchronous reset functionality built into the block memory. So to infer the block RAM's output register functionality, make sure you infer a synchronous reset. Now, just as I mentioned before, using more of the dedicated hardware resources will improve your device utilization, speed your design, and improve your power consumption, particularly when you consider that most FPGAs have unused block RAMs for many alternative design purposes, such as building ROMs, large-scale lookup table functions, such as a sine or a cosine wave generator, deep shift registers, and one of my personal favorites, complex finite state machines. Now, we described some of these applications as part of the Designing for Performance course. But the key here is recognizing that using the block RAMs for other purposes can free up hundreds of flip-flops and help improve your system speed and your power consumption. Also keep in mind that the easiest way to get the block RAM is to build it with a core generator and then instantiate the core into your design. Now, this is very commonly done because most synthesis tools will not infer the less obvious block RAM functionality. You should remember that the shift register LUT does not have a reset port, so if you build a local reset into your design, you will prevent some shift register LUTs from being inferred. If you have a local reset on the shift register in your code, the synthesis tools are left with one or two choices. They either do not add the shift register LUT primitive to your netlist, meaning they'll use a bunch of CLB registers to implement your shift register function, which is of course not what you want because this will waste flip-flops, or they try to emulate the reset functionality. Now, emulating the reset adds more logic and the design becomes slower as well as larger. Now, let's wrap up our control set discussion with the flip-flop resources with a short summary. In summary, control set restrictions can reduce your design utilization. This prevents all of your flip-flops from being merged into the same slice and can restrict some slices to holding fewer registers than might be possible. Now, your reset methodology can have a significant impact on your design efficiency, especially if you choose an asynchronous reset, okay? Because this can reduce, again, your device utilization, increase the number of writing resources that is used, which may also impact your speed of your finished design. For designs that are not pushing the limits of your technology, it is recommended that synchronous resets be used for all storage elements. But in most cases, we virtually recommend synchronous elements all the time. For more sophisticated designs, a mixed approach where only critical logic is explicitly synchronously reset and all other logic relies on the GSR is recommended. So in that case, you use the GSR to reset your entire design, and then you use local resets throughout your design when necessary. Just make sure they're synchronous. Also, using asynchronous resets should be used only when absolutely required. That is, when the clock may not be present. Now, there are some very useful resources available to you on support.xilinx.com. The Synthesis and Simulation Design Guide discusses some of these same topics. The XST User Guide is very helpful for example inferences of architectural resources as well. This is often what is most helpful to customers, so I'd strongly encourage you to check this document out. Likewise, to learn more about Xilinx primitives, check out the Libraries Guide. It discusses control signal precedence and functionality of the flip-flops in your device resources. Now, please take a second and give us your feedback on this recorded e-learning. All you have to do is click on the icon at the end of the recording to submit an evaluation. Finally, thanks for listening to this recorded e-learning on the 7 Series Slice Flip-Flops, Part 2. Again, my name is Frank Nelson. Thanks for your attention, thanks for your time, and thanks for your business.